the chloride is negative, iron becomes positive. That's all I was trying to get you at. Okay, so yeah, the iron is going from what we call an oxidation number of 0 to an oxidation number positive 3. The copper, I'm not going to ask, I'm just going to tell you this time. Copper is a positive 2 in this formula. What is the charge of it over here?
0.
It's becoming elemental copper. This is copper metal. And so it is a 0 charge. Now, I have to tell you, copper ions, when they're positive 2, they're blue. Like the color of the blue Gatorade. What's happening to the solution color here? I know it's pretty much filling up, but do you see the color difference? It's not blue anymore. When you look at the liquid itself, it's got kind of a yellow color. It's yellow because iron 3 ions are yellow. This is considered an oxidation reduction reaction. That mug just cracks me up too. It's a red ox mug. This is classified as an oxidation reduction reaction because anytime you have a reaction in which something's oxidation number, aka charge, changes, then there's a transfer of electrons. The copper is losing electrons. I'm sorry, I said that wrong. The iron is losing electrons. It goes from 0 to positive 3. When something becomes a positive ion, that means it lost electrons. Where are the electrons in iron going to? Can you tell? Where are the iron? Would you agree that iron is losing electrons?
They go to
They go to the copper. Yeah. And what we're going to find is that in redox reactions, when something loses electrons, there has to be something in the reaction to gain those electrons. Redox is about the transfer of electrons. Redox chemistry has a huge real-world application. There's several real-world applications. Combustion is a redox reaction. Redox reactions involve the transfer of electrons, also known as the flow of electrons from something to something else. Do you know of anything in life that involves flow of electrons? What do you know of that involves the flow of electrons? Like outside of science, like in real life, the flow of electrons.
Electricity.
Yeah, you got it. It's electricity. Batteries they work because of chemical reactions going on in them, and it's redox chemistry. We're going to study in Chapter 18 in this class. Chapter 18 is electrochemistry. We're going to find out how batteries work. You'll make a battery in that chapter, and that's all about redox chemistry. So it's a pretty interesting, real-world kind of an application. Can you see the board okay? I don't have the lights off in the front, but is it coming in?
Yeah.
Good. Okay. So yeah, that's what we're up to with redox. Now in Chapter 4, we're just going to kind of lay the foundation for what redox reactions are, how to identify one. If something has an oxidation number changing, then it's a redox reaction. They always go in pairs. If there's an oxidation, there must be a reduction. Because the electrons, when they leave one thing, they have to go to something else. That always happens. So yeah, it's kind of like the Bronston-Lowry theory, where one's an acid, one's a base. The same thing is true here. Something oxidizes, something has to reduce. Now, I'm going to put this up. I have a whole slide here that's going to have rules for how to come up with the oxidation number for an element. Every element in a reaction needs to have an oxidation number assigned to it. An oxidation number is very similar to charge of ions. I have always used the term charge. I'm going to turn the lights off so you can see it. Really, charge isn't quite accurate. It really should be expressed as an oxidation number. So oxidation numbers are assigned according to these rules for elements like the iron in the steel wool. The iron, before it was reacted, was just neutral iron. So it has an oxidation number of 0. For monatomic ion, the oxidation number is whatever the charge of the ion is. So like if I have the chloride ion, the oxidation number of that is -1. We always call it charge. It really is the oxidation number. Yeah.
Isn't chloride just an element, though?
Chlorine is an element.
Oh,
Chlorine is a diatomic element. That would have a charge of 0 or an oxidation.
Yeah, because it's
Chloride, yeah, but it gains an electron. So yeah, whatever the charge is, and if I gave you something like, I don't know, ZnCl2, you know that what we've called the charge, the oxidation number of chloride by the noble gas rule is a -1. And what I'm pointing at there, the periodic table, we just use the noble gas rule. Chloride is a -1, therefore the zinc has to balance it with a +2. That would be its oxidation. So those are monatomic ions. Do you have a question or? Okay. Whenever you have fluoride ion in a compound or fluorine in a compound, it's always going to have a -1. The reason that we single out fluorine is it's the highest electronegativity of any element. Always will take electrons toward it, which means it's always going to gain an electron. Even if it's sharing, it's still pulling the electrons more toward itself, which we're going to assign an oxidation number. As long as it's in a compound, bonded to something else. If you have fluorine gas, it's going to be 0 because that would apply to number 1. It's an element then. But when it's fluorine in a compound, it's going to gain an electron. Oxygen, you're going to always assume that it's going to be -2 when it's in a compound, but be on the lookout. Watch out for peroxide. Peroxide is the one exception that I want you to watch out for. Oxygen in a compound is not -2. What would be the oxidation number of oxygen and peroxide? It's -1. Yeah, you've got 2 oxygens bearing a -2 charge, so each O is a -1 in peroxide. That's an unstable oxidation state for oxygen, so it is pretty reactive, peroxide. You should probably already know that. Hydrogen is going to be a +1 as long as it's in covalent bonds. If it's bonded to other nonmetals, it's going to be a +1. Sometimes you can't have a hydride ion. In that case, hydride, I means it's negative. H can be a negative ion. But I don't think we're ever going to see that in this class. Just assume hydrogen, when it's there, is a covalently bonded atom. It's going to be a +1. So we have specific oxidation numbers assigned for 3 elements. And then the rest of the elements, you can pretty much figure them out. You can just determine them knowing these 3. We'll do a few examples on the next slide. A couple other tips for determining the other elements. Remember, the compounds have to add up to be neutral. So they have to add up with a total oxidation number for the compound of 0. So everything in a compound is going to have an oxidation number, but they always have to add up to 0. Polyatomic ions have to add up to whatever the charge on the ion is. All right, so let's try a few examples. We're good with this? What are the oxidation number of all the atoms in these terms? And I didn't erase one of them. Carbon dioxide. When we look at this thing, we don't think of carbon dioxide as being something that has charges in it. It really doesn't. But you can assign oxidation numbers to these 2 atoms. And we have a rule just for oxygen, so we're going to apply that rule. The oxygen we're going to assume to have a -2 oxidation number. What would that make the oxidation number of carbon? +4. Yeah, the whole thing has to add up to 0 for oxidation, so if you have 2 -2s, then the carbon's got to balance it with a +4. Now, if I could just show you what I mean by that, if you have covalent bonding like this has, the oxygen is more electronegative than carbon is. So the oxygen has its 6 electrons, and then the carbon is offering it 2 electrons in the double bond. Oxygen being more electronegative yanks the electrons away from the carbon that way, and that way. So it's like the carbon is losing its 4 electrons because the oxygen's yanking them away. So even though this is not ionic, it is a covalently bonded molecule, the carbon is feeling like it's losing its 4 electrons, which gives it a positive 4, not charge, oxidation number. The oxygens are gaining the 2 in each case of the double bond. This oxygen is gaining 2 electrons. That oxygen is gaining 2 electrons because of the unequal sharing. That gives the oxygens a negative 2 each. So that's what an oxidation number is about. Now, in sulfur hexafluoride, one of the oxidation numbers are these two. Which one is more obvious, the S or the F? The F, because you have a rule for F. F, when it's in a bond, is always negative 1. What does that make the oxidation number on the S? Positive 6. Yeah, Brian?
So basically, it's just like when the F is negative 1, so that means it's negative 6 as a total. Like S just becomes plus 6.
Yeah, you have to make the whole thing 0. Yeah.
So like, it's because the F pulls away.
That's right, yep. You have an S with 6 fluorines around it. Each one of those fluorines is yanking the electron. Fluorine is very electronegative, so it's yanking the electrons away. So sulfur feels like it's losing all 6 of its valence electrons.
But it really doesn't.
Right.
So like, charge-wise, it would actually be...
Still neutral.
Still neutral?
Yep, yep. But it's assigned to oxidation number of positive. This is a pretty unstable molecule because the sulfur is having all its electrons yanked away from it. It gives it like a sensation of being too positive, so it's going to try to react quickly and find something to bring its oxidation number down. Things are more stable when their oxidation number is close to 0. So that means this is pretty unstable. With a positive 6 oxidation number, that's going to try to find something there. Andrew, you have a question?
Yes. What would you do if there was, if you didn't have something with a rule in it?
You're not going to have that.
Okay.
You're always going to have something that's got H, S, not S, that's not the rule, H, F, or O. Yep.
Okay.
Because you won't be able to determine it. Like, let's say we have Si2 or something like that. I'm not going to give you Si2 and ask you to find the oxidation number of those things. I think it'd be more obvious than that.
Okay.
So yeah, I'll give you the rules. Use those rules, and those the examples I give are going to stay within those rules. Okay. All right. Now we have a polyatomic ion in this one. What are the oxidation numbers? One of these you can know right off the bat. Oxygen is negative 2. Now the question for nitrogen is this. What does the nitrogen have to be so that when you add it to 3 oxygens, you get a negative 1? These have to add up to negative 1. What does that nitrogen have to be? Positive 5. That's how we do that. What plus 3 times negative 2 equals negative 1? And that's a lot of numbers and words in there, but yep. So 1 plus negative 6 is negative 1, that's positive 5.
0.
This one?
0.
Yeah. Was I trying to mess with you on this one? I was trying to make it look like carbon monoxide, but you know that capital C, lowercase o is cobalt. That's got a, it's neutral. I don't indicate any charge on it. That means if it doesn't have a charge, its oxidation number is 0. And then finally, I'll put a stinker down here too, potassium dichromate. Potassium is positive 1, because you know the potassium ion is always positive 1. I agree. Chromium, though, it can change. What?
O's are negative 2.
You know the O's, though, yes. So kind of that chromium is sandwiched in there. Can we figure out the chromium charge?
12.
Negative, or plus 6.
It is positive 6. Why? Because there's 2 CRs. So yes, the potassiums add up to positive 2. Yes, the oxygens add up to negative 14, 2 times 7. So the chromiums have to balance out all that to make the whole thing 0, which is positive 12. But there's 2 CRs in there. So each one is positive 6. Is my glassware in the way?
You remind me of the Bruce Spears guy, because you like look at the camera and you're like, wow.
Yeah, that's a good guy. I like him. That's on the Blue's Clues. Yeah. Okay, any questions on how to assign oxidation number? All right. So now what we're going to have to do with oxidation number is we're going to have to learn